Given a vector field v equals the position vector, what is the outward flux over the surface area of a cube whose faces are the planes x equals plus or minus 1, y equals plus or minus 1, and z equals plus or minus 1? Calculate directly and also show it from Gauss's theorem. So in this problem, we'll be finding the flux of a vector field through a surface. And you can imagine flux as kind of the flow or how much of the vector field passes through the surface. And some of the applications of this might be finding the flow of water through a section of pipe, or maybe finding the electric flux, which is very useful in electricity and magnetism. And so flux is essentially just a normal vector surface integral. And so we need a vector v, a vector v, which is going to be the position vector in this case. And we also need a surface S to integrate over, and that's going to be our six-sided cube. And that's a 2x2 cube. We have our 6 faces that will have an area of 4 each, and it's centered at the origin. And the last component of this surface integral, this is the formula for the surface integral, is n hat, and n hat is the normal vector to the surface. So you can imagine if we have a surface is a plane, the normal vector will be perpendicular to that plane, and it's a unit vector, so it will have a magnitude of 1. And since this integral is an integral over the entire surface, but it's hard to find a formula for a cube as one continuous surface, we're just going to treat each of the 6 faces separately. So let's start with the side of the cube at x equals 1, and that will have a normal vector pointing away from the origin of positive x hat. And just plugging things into our surface integral, we can see this dot product here simplifies things a lot. We end up with an integral of x over a 2x2 square in the x equals 1 plane. Since x is a constant, that's just plug in positive 1 for that, and that becomes a integral of 1 over that square. And just as we would expect for surface integral, the result is just 4. It's the area of the square. Now let's try that with the square opposite of the side we just did. Here, x equals negative 1 is the plane we're looking at, and our normal vector is negative x hat. So the negatives here end up canceling out. You can see we do the dot products and end up with negative x, but plugging in our constant, that becomes positive 1 again. And so it's, yet again, just an integral of 1 over this 2x2 square, so we get 4 again. Now there's nothing special about those two sides of the cube, and if we go back to our initial problem, we see the surface is exactly the same if we switch x to y, y to z, and z to x, and wait, there we go. The surface is exactly the same if we switch x to y, y to z, and z to x. And the same thing is true of our position vector, v. And so x times x hat goes to y times y hat, etc. And we can see that the value of this entire surface and this entire vector, they're both invariants under this transformation we describe, or there's symmetry there we can use. And we actually get to the point where we can assume that the value we get for one side is the value for all 6 sides of the cube. And so that gives us our flux as 6 times 4, and that gives us 24. And I'll put the math on screen for you to pause and take a look at if you're not convinced over here. And you can just pause that if you need to convince yourself, but it works out quite nicely, and we end up with the same value for each side. Okay, now since our cube is a closed surface, we can now try to do the same thing with Gauss's theorem. And so you can see for a closed surface S surrounding a volume V, we have the surface integral over the closed surface of our vector times the normal vector to the surface, or our vector dotted with the normal vector, is equivalent to taking the volume integral of the divergence of this vector, and that's the divergence right there. And so this left-hand side with the surface integral, that's just the flux through our cube. We just found that earlier. The circle in the integral sign just indicates that it is a closed surface. And so on the right-hand side, we can do the same thing and find the flux now using a volume integral of the divergence. So let's try that out. And the formula for the divergence is here. We'll be taking the x derivative of the x component of our vector, the y derivative of the y components of our vector, etc. And for our vector, that becomes 3. The divergence is 3. And so this just becomes a really simple volume integral because we plug in 3 for our integrand, and it becomes an integral from all of our coordinates going from -1 to 1 of 3 dx dy dz, or that's 3 dv if we're looking at it in terms of volume. And so we can carry this out either coordinate by coordinate. Dx evaluated at those limits becomes 2, and then we add another 2 and we do y, and it ends up being 3 times 2 times 2 times 2 is 24. Or we could just do this purely in terms of volume and say, okay, an integral of 3 dv is just 3v, and v here is not our vector v, that's the volume v. And so our volume of a 2 by 2 by 2 cube is just 2 to the 3rd power, that's 8. And so 3v is 24. And as we would expect, this answer and this answer for either of those ways of carrying out the volume integral, they're the same as our surface integral solution. And so this is what it looks like to compute the flux for a vector over a surface, and it's a good example of how useful Gauss's theorem can sometimes be to do this a lot more quickly.